Uranium powers nuclear reactors. It fuels nuclear weapons. It is the most energy-dense material we have ever discovered. But here is the secret the world rarely talks about. Raw uranium, straight from the ground, is useless. It won't power a single light bulb, and it won't trigger a single explosion. To turn a rock into a godlike power source, you have to do something nearly impossible. You have to find the active atoms hidden inside the stable ones and separate them one by one. It is the most expensive, most guarded, and most dangerous engineering process on the planet. But how do you separate two things that are chemically identical? How do you filter an atom that is only 1% heavier than its neighbor? And why is this single industrial process the red line that decides which nations are allies and which are targets? Today, we are uncovering what exactly is uranium enrichment. Natural uranium is like a deck of cards, where only one card in the entire pack is an ace. The uranium we mine is 99.3% uranium-238. This isotope is stable. It's essentially dead weight for a nuclear reaction. The ace we need is uranium-235. This is the only isotope that can easily undergo fission to release energy. The problem? U-235 makes up only 0.7% of natural uranium. To make it useful, we have to increase the concentration of those ace atoms. This is the definition of enrichment. But you can't use chemicals to separate them because they are chemically identical. They look the same, they act the same. The only difference is their weight. Imagine trying to separate two types of sand that look exactly alike, but one grain is 1% heavier than the other. To do this with uranium, scientists first turn the solid rock into a gas called uranium hexafluoride, or HEX. This gas is highly corrosive and dangerous, but it allows the atoms to move freely. Now, we can use physics to do what chemistry couldn't. Since U-238 has 3 extra neutrons, it is slightly heavier. If we spin that gas fast enough, the heavy atoms will be thrown to the outside, leaving the lighter, precious U-235 in the center. This is the gas centrifuge. It is a marvel of engineering that spins faster than the speed of sound. As the hex gas enters the cylinder, the centrifugal force pushes the slightly heavier U-238 toward the wall. The lighter U-235 stays near the middle, but the separation is tiny, almost microscopic. To get enough U-235, you need thousands of these centrifuges linked together in what is called a cascade. The gas passes from one machine to the next, becoming slightly more enriched at every single stage. It is a slow, grueling process that consumes massive amounts of electricity and precision. This is where the world starts to get nervous. The level of enrichment determines the destiny of the material. Low-enriched uranium. This is enriched to about 3% to 5%. This is the sweet spot for nuclear power plants. It's enough to create a slow, controlled heat to boil water and make electricity. Highly enriched uranium. If you keep spinning those centrifuges until you reach 90% U-235, you no longer have fuel. You have a weapon. At 90%, the material is so concentrated that it can sustain an uncontrollable chain reaction. The difference between lighting a city and leveling one is simply how long you leave those machines running. This is why enrichment is the ultimate red line in global politics. If a country builds a civilian enrichment plant for energy, they are only a few technical steps away from building a bomb. It is the ultimate dual-use technology. Owning a centrifuge cascade means energy independence, but it also means a seat at the table of global power. It is a technical achievement that carries a heavy price. constant surveillance by the rest of the world. Uranium enrichment is the process of taking a common rock and refining it into the most powerful fuel in existence. It is a testament to human brilliance and a reminder of our capacity for destruction. We've learned how to unlock the atom. The only question left is, are we smart enough to handle what we found inside? Let me know in the comments. Should the world move toward more nuclear energy, or is the risk of enrichment too high?